So, our project, this is Jan and Dallin. We did our system project on quadcopter control systems. So this is a real basic what a quadcopter is like. You have just usually it's four rotors because it's a quadcopter, and then each rotor has a propeller and a motor at the end of it. So the propellers on opposite corners spin in the same direction, but then they spin in alternate directions from the propellers directly next to them. This is due to momentum. So if all the propellers were spinning the same way, the quadcopter would actually just start rotating in the air, and it would be really hard to control. So in order to cancel each other out, they rotate in opposite directions. So we have some. So this is our plant is the quadcopter itself. So here's some of the quantitative measurements for this. There's your force of gravity, your mass, which will give you the weight of the quadcopter, the distance from the center to the motor. These are just numbers that we found to be typical on some quadcopters, smaller scale quadcopters. So mass like 0.75 kilograms, distance from the center of the quadcopter to where the rotor is, 0.26 meters. There's a moment of inertia about each of the X, Y, and Z axes. So you have 0.019688 kilograms per kilogram meter squared for both the X and Y axis, and then 0.03938 kilograms meter squared through the Z axis. We found these through a report where they did experimental data. And then you have a propeller force constant for each of the propellers, as well as propeller torque constant, as you can see down there. So there's four main equations for the actual system. You have your roll rate, your pitch rate, your yaw rate, and then your thrust force. So that's what these are here. Basically, you have a proportional constant, which is what the K's are equal to, and then the omegas is the angular velocity of each of the individual rotors. Here's a simple block diagram. So for our system, we just used we chose to use PID for the control system to keep it simple. So you have your reference point, and then you have your PID controls, your proportion, integral, and derivative controls. They go into the plant, and then that gets sent back to the reference to check, and then you get your output at the end. So we made, so for as far as feedback comes, there's various things you can use. Typical things are an electronic speed controller. That's what you would use to control the speed. That's what gets the signal put in, and it controls the speed of the actual rotors. And then there's also an accelerometer that will measure and tell us what our pitch and roll and yaw is, basically give us the position of the quadcopter in the air. For reference, we have our transmitter. So every quadcopter has a controller. They're very similar to this. So you'll have two sticks. One stick on the left will control the speed that the rotors are flying in for your vertical, and then this will also rotate it in the yaw direction, and then this one will move it in a pitch or a roll direction. So that's what our transmitter would do. And then so on the actuators for the signals, it gets the signal from the transmitter and goes to the electronic speed controller, and then the actuator would be the rotors themselves. That's what causes the quadcopter to actually perform and take off in the air. So we made a fairly simple Simulink model. We got some help from sources on the internet on how to set this up. So basically you have your reference positions here, and then you have this is your controller, so this would control what each thing is doing for pitch, roll, vertical position, stuff like that. And then this is where it would go send the controls to the actual motors themselves. And then with a step function, we ended up getting this plot. This plot just shows the different rates. So you have your pitch reference in purple, your roll reference in green, your vertical reference in a light blue, and then your altitude reference in red. And so that's what we've gotten for our plots. And then so for errors for the system, what we determined for errors would be one with a PID control system, trying to measure your position if you were trying to get to a certain reference point, and say you had a disturbance. So there's a lot of disturbance of quadcopters, such as noise in the system, and the biggest one would be physical disturbances such as wind and obstacles. So it's really hard, especially for wind, for a PID controller to take that into consideration and adapt and modify itself to solve that problem. So one of the solutions to fixing this actually would be to add into an adaptive control system. So an adaptive control system would take into account all those uncertainties that are going to affect the system as a whole, and then it would fix them and improve so that the quadcopter would be able to maintain its system status while it's flying. And that's it. Thank you.